Many thanks to the organizers for the invitation and also the invitation to speak. So thank you. This is joint work with Jason Atnip, Cecilia Gonzalez-Tocman, who is down the back in the audience, and Sandra Vienti, who I think is teaching at the moment. Can you hear me okay down the back if I speak at this volume? Yeah, okay. Okay, so I'm going to start with an outline of related deterministic results as a warm-up, and then we'll get on to the random part. So there's a well-known stability theorem by Gerhard Keller and Colangelo Liverani from 1999 for transfer type operators. And 4 years later, this was applied to open systems where you have a closed system and you introduce a small hole, and that is the perturbation. And Liverani and Deschamps used this to show that a thermodynamic formalism persists under the introduction of a small hole. Then 10 years later, Keller and Liverani got back together and made a refined version of the 99 paper by proving a first-order result for the behavior of the top eigenvalue of the transfer operator under perturbation. And in that paper, among several applications, one of them was to provide a derivative for the escape rate with respect to the hole size. So the idea is that you have a hole that is shrinking to 0 size. The escape rate is also going to 0. And what is the rate at which this happens as the hole goes to 0? And then a few years later, Gerhard Keller made a nice spectral approach to extreme value theory using this first order result. So what I want to talk about are random versions of these topics, where we have, as many people have given very nice talks on, so it's very helpful for me. You have this usual kind of map co-cycle driven by some base dynamics, or in some cases, I'll try and mention it when it comes up, that you don't even need the base, it can just be some sequence of maps. Okay, so let's start I have about 5 slides on deterministic maps. So you've got the setting is going to be piecewise monotonic, usually expanding interval maps. We have some weight, and you make your transfer operator in the usual way. Now, in order to get a thermodynamic formalism, you ask things like T is covering. So if you have some small interval, this is eventually stretched over the entire interval by iterates of the map. And you need your weight to be what's called contracting, and I won't say what that is here, but I will later for the random case. And then Liverani, Sassol, Vienti, all of whom are attending this workshop, showed that you have a conformal measure that satisfies this backward adjoint eigenequation. You have an eigenfunction satisfying the forward equation, and you can combine these to get an invariant measure that has exponential decay. So all these objects are put together, we're going to call a thermodynamic formalism. And so one of the more common situations is where the weight function is just 1 over T prime. In that case, the conformal measure is Lebesgue, and in order to get the phi, you can identify with the invariant density. And in order to get contractivity of your weight, you just need sufficient expansivity of your map. Okay, so now into such a setting, you introduce a small hole. And you ask, what happens to my thermodynamic formalism when you do this? So your open transfer operator now, what you do is you kill anything that is in the hole, and then you iterate as per usual. Now, in this paper, Liverani, Deschamps, 03, they showed that if the hole is small enough, then by perturbation theory, you get a unique ACCIM, and you can combine this with the backward adjoint conformal measure to get an invariant probability measure on the survivor set. And this is a unique equilibrium state, and this has exponential decay. So everything is nice. You have this thermodynamic formalism for your closed map, you puncture with a small hole or holes, and you retain your thermodynamic formalism. Okay, and then moreover, in this paper by Keller and Liverani, 09, they ask what happens as you have a sequence of holes that you send to 0, And they consider this ratio here, which you can think of as a derivative of escape rate with respect to the hole size. So this gap is effectively the escape rate. And as you send epsilon to 0, you have a formula. So this is the hole is shrinking around a point C, and this ratio is 1 if the C is aperiodic. And if it's periodic, you get a formula that depends on the expansivity of T around the periodic orbit. Okay. Now some basic recap on extreme value theory. So apologies for all this basic stuff at the beginning, but it's, I think, a useful warm-up. So let's say you have the simplest possible situation. You have IID random variables. You make a new random variable, which is the maximum of those you've seen up to time n. And you're interested in what's the probability that you exceed some sequence of thresholds as n increases. And so in the IID case, this is of course easy to calculate. You can just take powers of the individual probabilities. You can write in terms of this complementary probability. So now this is the probability that you observe the extreme event. And so now, in order that you have a sensible limit as you take n to infinity, you have to scale these thresholds z in a particular way. And one of the more common ways is to say that the probability that you exceed or that you have an extreme event by the nth step is going like t over n for some t. And now you can just substitute here this with t on n, and you let n go to infinity, and you get your basic exponential extreme value law. Okay, so let's see how this works with deterministic dynamics. We have to replace these psi j with something, and so what we do is we have an observation function, and we evaluate it along an orbit of t, and this generates a sequence of real numbers. And again, we ask, what is the likelihood that you don't exceed this threshold, that you don't see an extreme event up to time n? And again, of course, the zn's have to increase with n, and they are increasing toward the maximum of this observation. That's typically how things are set up. And the same trick is played by Keller in his 2012 paper, where this is the probability that you exceed your threshold. So this is analogous to what we had over here, this same scaling. And you ask that this goes like t over n for some scaling t. And then what you can show using this first order perturbation theory from Keller-Livrani 09 is that this goes like e to the minus theta t. And the theta, you have a formula that is similar to the one I showed you earlier for this theta, which is known as the extremal index. So if this c, okay, if the maximum of your observation is an aperiodic point, then your theta is 1. And this is analogous to what we had here, because here the theta was 1. Okay, but if you're periodic, then you get this expression concerning the expansivity around the orbit. Okay, so now finally random dynamics. The setup is exactly the same as Cecilia and Davor and other people have talked about. And we're going to concern ourselves now with transfer operator co-cycles, where we have a sequence of distinct transfer operators. And yeah, here is some, I guess I'm focusing here on thermodynamic formalism, because this is the main topic of the talk. And there's been quite a lot of work over the years on random thermodynamic formalisms. And so I'm not going to go through all this, but I maybe just highlight that one of the novel things we're doing here is to work with discontinuous maps, which we will need when we treat open systems and extreme value theory. Okay, so to make our random open system, we take our random closed system, like many people have talked about, and on each omega fiber, you puncture with a random hole or holes. And of course, any trajectories that are mapped into the sigma omega hole by T omega, they are terminated. The epsilon, we have these holes, we're also thinking of sending them to 0, and so epsilon is some parametrizing sequence. If the holes are relatively large, then in this paper, which I'm not talking about today, we show that you get a thermodynamic formalism. But today, well, it's not sufficiently, it's relatively large. Okay, so I guess this is not something that needs to be very small. So it cannot be too large, but let's say moderately large, something like this.
You cannot apply perturbation theory, for example.
You cannot, yeah.
Considering this hole so small that behaves like.
So this is using different techniques. In fact, it's extending the techniques of Livrani-Momme-Deschamps 3. So you have these good and bad. But what I'm talking about today are small random holes. So we want to send the size of the holes on each fiber to 0 and see what happens. Okay, so the first, what I'm presenting here on this slide, I think, yes, this is the one. This is, I guess, one of the key abstract results for the paper. And this is, in a way, extending the key abstract result from Kettle-Livrani 9 to the random setting. Although I have to say the extension to the random setting was not really clear at all. So this is our version. So at this stage, these don't have to be transfer operators. They're just linear operators that are going to satisfy several conditions. And we don't even need statistics in the base. So this is just some sequence of linear operators. Okay, so they should be bounded in that way. This next condition, I guess, is pretty strong, and later we'll have some conditions that to ensure it's satisfied. But this is saying that we have this nice equivariant family of functions phi that satisfy forward equivariance, and measures nu that satisfy backward equivariance. And these are like our top, these are our top Osiledit spaces. And then we have the rest. So if you hit some function with L, then you get this projection onto the top space, one-dimensional space, and then you have a rest, a contraction. Sorry? Yeah, yeah. Sorry? Yes, yes. So the question was B omega star is the dual of the Banach space. Okay, now we have to say that this family is close to the original cocycle, and one of the ways we say this is through this quantity. So this should go to 0 for almost on every fiber. On every fiber, this should go to 0. But we don't here have uniformity between fibers. And this is another way of saying that, that these perturbations are close. So here we would take a supremum over test functions, and here we have the specific test function, which is our equivariant family. And the result we should get is somehow commensurate in the sense that the limit of this ratio should be finite, again, fiber-wise, just fiber-wise. This condition is about decay of the Q. So the Q should somehow be killing, eventually killing what it acts on. And so here we are, instead of acting like here in the delta, notice we are dividing by the delta here. So here we are acting on the phi, but instead what we do here is we act on we pull phi back, or we look at the phi n steps in the past, and then we push it forward n steps. And this should be sufficiently decayed so that in the limit, as n goes to infinity, this quantity goes to 0. So this is a statement about how Q should decay. And then some technical limit exists that I don't want to write on this slide, but I'll tell you about in a simpler setting on the next slide. So if you have all this, then the result, you have some information fiber-wise about the first order behavior of the leading Lyapunov multiplier. So the delta is a measure of how close your operators are, and this is a measure of how much your leading Lyapunov multiplier is perturbed. Okay, so you could think of this as a rate of perturbation of your top multiplier with respect to how close your operators are. And you get this, well, I guess not yet explicit quantity on the right. But this is for every fiber. Okay. All right, so let's now apply this to random open maps. So now my L's are going to be like before, transfer operators for a closed map. And my L omega epsilons, they are going to be the transfer operators for the open map. And this is just the omega version of the definition I gave you earlier. It's not hard to show that this quantity delta that I talked about, this is just the top multiplier multiplied by the omega measure of the hole. So you just look at the hole size on the omega fiber. And on the previous slide, I wanted this, let me just remind you, I wanted this delta to, where was it? Actually, I didn't write that anywhere, but this delta should go to 0. And so that corresponds to our hole sizes going to 0 on each of the fibers. Okay, and now these Q's. So on the previous slide, I had this Q omega hat K, and now I add an epsilon here. And this is going to be these are just numbers, they're just scalars between 0 and 1. And in this context, you can think of this as the probability that you start in a hole, K plus 1 steps in the past. You then start iterating your random orbit. You avoid the holes for K steps, and then you land in the hole on the omega fiber. And you condition on landing on the hole in the omega fiber. And so what you need is that as you send epsilon to 0, the limit of these numbers exists, and that whatever that limit is, I denote by the Q omega hat K. Okay, so if I have that and the dot points on the previous slide, then it's essentially a matter of substitution into the abstract theorem I just showed you to have a statement about how the top multiplier is varying with respect to the size of the holes on each of the fibers. And
why almost every opener? I thought this was for every opener.
I mean, it's almost everything is almost everywhere. Oh, you mean because I said sequential before?
Yes. Sequential stuff.
Yeah, maybe I've kind of mixed the terminology here. I think at this stage we're not using any ergodic theory, so I probably could have. Yeah, I think you can have every there. Okay, thank you. However, in the paper it's probably stated this way because, yeah, it's a random system. Yeah. Okay. And so I'm going to call this theta omega later because this is like an omega-wise version of the extremal index. All right, so escape rates, I'm going to call, for holes at level epsilon on the omega fiber, this is going to be my n-step survivor set. So I'm starting at fiber omega, I run my system, and I should avoid the holes on the successive fibers for n steps. And then you can define an omega fiber escape rate in the usual way. You just do 1 on n log that measure. And because the size of these sets is growing basically like lambda omega n steps along the cocycle divided by lambda omega epsilon n steps along the cocycle, it's not too hard to show that you get this, I mean, that this measure, the log of this measure is given by the difference of these logs. And then Birkhoff then gives you, shows you that this is non-random. Now we're using, now this is almost everywhere.
So this measure is just some translation invariant ergodic measure on omega?
Yeah, it's invertible and it's ergodic. That's it. Yeah. So the question is, what was sigma? So the action on the base is just invertible ergodic. Okay, and so now we can again use theorem A, the first order result, to talk about a derivative for this escape rate with respect to the hole size. So again, we need that these limits of these q hats, of these numbers, exist. We have to put a little control on how the hole size varies from fiber to fiber, but it's pretty general. You can think of this twiddle as being equal, if you like. So the t is just some essentially bounded function, and the kappa is just something that goes to 0, whatever rate you like. And we also need a little bit more, basically for Birkhoff, we need a little bit more control on how much the top multipliers can vary with respect to the hole size, but again, it's not too strong. This is something integrable. And then you can take this limit. So in this limit, this is going to go to 0, this is going to go to 0, but you get a sensible limit as you send all the holes on all the fibers to 0 size. And
this condition is not very easy to check.
This one? The last one. Yeah, I guess if you were checking it, you would probably use a constant a, but yeah, I agree, for an integrable a, it's not so easy.
For all omega, for almost all omega, for this condition, last condition, for almost all omega?
Yeah. Okay. So now to the extreme value theory. So how do I set this up? So again, I start with a closed random system. This is going to generate the underlying statistics. So I assume that I have my thermodynamic formalism. I have my random conformal measure, equivariant densities, and equilibrium state. And assuming this is, this is not so easy, it's easy to say, but not so easy to get. And when we started this work, we were targeting the extreme value theory, but then we realized that for discontinuous maps, there didn't really exist any technology for showing thermodynamic formalisms in the random setting. And so we had to go back a few steps, and that was, so this paper is doing that, is giving us this statement here. So for the extreme value theory, to set up our statistics, we're going to run our closed process. And the trajectories will be distributed according to these fiber measures. So you have some initial condition in your domain. You run out your random orbit, and you start observing with some random observation functions. And this is going to generate a sequence of real numbers that you want to talk about extreme value statistics for. So we want extreme value laws for sequences of real numbers like this. And in particular, limiting laws of, so what is the likelihood that n steps along for the first n steps along your random orbit, your random observation functions don't exceed some random thresholds. And now maybe I take a little diversion to say about something about the modeling. So in particular, why should these...
Can I ask you
Yes.
the fact that the observation is random, okay, you can do it, but you have some...
This is a great question, because I'm just about to explain. So the question was why
do I allow
yeah.
it?
That's right.
The fact that you can. That's fine.
Okay. Okay, so random observation functions that would, for example, allow you to model situations where the observation depends on the environment for whatever reason. So maybe it's some physical apparatus and it's affected by the environment, and that would allow you to model that. Why would you have omegas on your thresholds? Okay, so maybe you're interested in temperature statistics of the ocean off Sydney, and you're a meteorologist or a climate scientist, and you know that the water is warmer in the summer than the winter, So you're not so interested in the absolute temperature. What you're more interested in are anomalous statistics. So I'm thinking here of omega as the passage of time. And so what you would do is on the 1st of January every year, you would measure the water temperature, and you would do that for many years, and you would subtract this mean. And in this way, you could make anomalous statistics. You would do that for 1st of January, 2nd January, 3rd January, and so on. And so what you would then talk about is the water warmer than it should be for any time of year, winter or summer. This is also done by economists. So if they talk about unemployment rates, they have these seasonally adjusted unemployment rates. It's known that you have this economic cycle, and they adjust for where you are in the cycle. On the other hand, if you are a fish, or you live in a coral community, then you don't care. All you care about is the absolute temperature, how hot the water is. And so it's the absolute temperature of the water that counts. And also, if you're an unemployed person, you don't care that at this part in the cycle, unemployment is more likely than not. You just care that you're unemployed, and what is the likelihood you get a job soon. And so in both those cases, you probably would want to use non-random Zs. Okay? So I think there are points both ways. And our theory doesn't require both or either, in fact, of randomness on the observation function or the thresholds. But you can do them. All right. So as is fairly standard, we make the identification of sets in the phase space where your observation exceeds the threshold. We think of these as holes. And so we define our hole. Now with this notation H, we define the hole to be the points where you exceed. And then we can write this in terms of, instead of using observation functions exceeding a threshold, we can write this as orbits avoiding holes for n steps. Right. And now let me give you I have a few sketches of some of the key steps. So this is what we want to estimate. We want to estimate the likelihood that your random trajectory is avoiding the holes for n steps. And so you can write this measure as an integral of functions that are indicator functions on complements of holes on various fibers composed with the relevant number of iterates of the map.
So when you say holes, are these functions h omega maximized at a point, or are they just general BB functions? Is it necessarily a hole?
This is a hole, but
no, but I mean you had it as h bigger than a number. So does that define topologically a hole?
H.
Or is it just a level set to be very extreme?
So H should be continuous, and then the super level sets cannot be too complicated.
Okay. It's not just a general BB function.
No. When I show you the theorem, we will have a hypothesis on how many connected components the holes can have. Yeah. But it's more than one. Yeah. Okay, and then we can squeeze in here using the backward equivariance of the nu. We squeeze in L iterates of our cocycle. So we compensate by sending this omega to the future, and we also compensate by dividing by the top multiplier. So that's just using backward equivariance of the L's. Sorry? This one? This is the top multiplier of the closed transfer operator cocycle. So I have to go back quite some way to like here, for example, or here. But without the epsilons. This I mean, lambda satisfies this property.
But what is lambda omega and subscript n? Subscript n multiplied?
You go along the co-cycle n times. I see your question. Okay, yeah. So lambda, yeah, it would be lambda omega multiplied by lambda sigma omega multiplied by etc. Yeah. Oops. Okay, and then you can stare at this and you notice that this is simply the open operator co-cycle acting on the full indicator function. And so the question becomes, how does this grow? How does this grow relative to 1 over this? And well, this is going to grow like its top multiplier, so you get this quotient of multipliers. And because we had this, if you remember this capital Q, which was decaying, that's what's involved in this exponentially lower order terms that I don't write here. So now when you take this limit, this is not so obvious because you have n going to infinity, but simultaneously the epsilon n's are getting small, and this is what we need to control. So to estimate this, I mean, roughly speaking, we follow the proof of theorem A, but it turns out to be a bit longer. Maybe this is giving you the best indication of how things go. So this is the expression I had from corollary A, which was the application of the abstract theorem to the random open setting. And on the previous slide, I had lim epsilon goes to 0 of this equals this, and now I've just deleted the limit and put a approximate. And now if you just rearrange things, just pushing things around, you can get this equivalent expression. And now this is what we want. I mean, in one step, we don't have the n's yet. And then with Taylor, you write this as this is to first order in whole size equal to e to the minus whole measure times theta omega. Okay, so now going along to estimate this, we...
Epsilon tends to 0 and capital N stays fixed?
No, n is going to infinity and epsilon n is a special sequence that at the same time goes to 0.
The product remains fixed? Or?
No, it's more, you need... The epsilon n, in fact, epsilon n is just a parameter, really. So there's no...
It's sub n.
It's sub n, yeah. It parameterizes a sequence of holes that must shrink at a certain rate, which I've sort of foreshadowed but not written explicitly yet. Yeah, that's LaTeX, I guess. Yeah. Okay, yeah. So to estimate what we want to do here is go along our co-cycle and go along our co-cycle, and you can see, I think, from here what happens when you go along your co-cycle is you'll have the products of exponentials, which are exponentials of random Birkhoff sums. So in here you will get a random Birkhoff sum, but it's not exactly a standard Birkhoff sum or random Birkhoff sum because the terms themselves have n's in them. So you need to do a little more work to deal with this n variation in your Birkhoff sum. And there are higher order terms I'm not showing you here that you also have to show can be neglected. But anyway, when you do all that, then here's the theorem. So you need some, a bit more uniformity than we had before. So, okay, your operators are bounded in this sense, your phi's are bounded above and below, and the Q is decaying now at this specific rate, so at a kind of summable rate. And now, when I talked about the extreme value theory from Keller, he had this parameter T that you choose and you fix, and then you generate your extreme value law. But we are random, so we don't have just a single scalar. We have a function of omega. So we have the scaling function that is essentially bounded. We have our random observations. We have our random thresholds, and we need to scale. We need to choose the z's in a certain way, and we choose them according to the same kind of ansatz as before, the measure of, so the likelihood you exceed goes roughly like t over n. But now the t it depends on the fiber. And we also add in, we went a little bit further, so we have this error term, which is bounded and goes to 0 with n. And this error term lets you treat a few more examples than you could otherwise. Okay, and then what you get is that you can take this limit now, and what you get is this for your right-hand side. So it's non-random. We're really assuming now a base, statistics of the base. And it's similar to what you had before, but different. So for compare this, and let me emphasize, this is for almost every omega. Okay, so this is again non-random, but so the left-hand side is in principle random, but the right-hand side is not. And this is quenched in the sense it's for every fiber. If you compare this, if I just go back to remind you what was in Keller, so there you have a single conformal measure, single observation, single map, single set of thresholds, and you have e to the minus t theta. Here we have e to the minus, well, we have to integrate over the various t's and the various thetas. But in form, it's not too far away. Okay. All right, this next slide, I just briefly say something about random hitting times. So you can get, if you scale the first hitting times to a sequence of holes in a nice way, then you can get a fairly cheap asymptotic result.
Maybe I got lost. Theta has some formula, no?
Theta, which one? The random one or this?
The deterministic one.
The deterministic, yeah.
But in the random one, do you get some formula too?
Yeah, it's the same as I had before. So it's the 1 minus infinite sum of q's.
Okay, this q's.
Yeah, the q's, yeah. Okay. Yeah, so now we think about a forward sequence of holes, which I guess have been there all along, but I haven't really been speaking about making explicit really this forward sequence. So we collect them up and use this calligraphic age. And then you can say, okay, I start at some x and some omega, and then I run my random orbit, and I ask, what is the first time that I land in a random hole in the future? And so that defines this function tau, which is just giving you a number, an integer. And then if you, okay, we already have this scaling. This was on the previous slide. I guess on the previous slide, I talked about scaling the likelihood that you have an exceedance. But remember, exceedances are just like holes. So what I'm writing here is completely equivalent to what I had on the previous slide. And if you, now you can ask about what is the likelihood that your hitting time multiplied by your hole size is greater than some arbitrary scaling. So what is going on as n gets large, your hitting time goes to infinity, your hole measure is going to 0, and if these are scaling the right way, then you can make sense of this question. So if I just substitute this into here, it becomes this, and then what you're asking here is what is this set here? What the set of points that last that don't hit a hole for n steps? Well, that is just your n step survivor set, and well, we know how that the size of that set is given by lambda omega n over lambda omega epsilon n, or I think the reciprocal of what I just said. And so you can apply the extreme value theory I had on the previous slide immediately to get that as you send n to infinity, this likelihood has the same law. It's really just a corollary of what I had on the previous slide. All right. Okay, so now I want to start talking about examples. And so far I assumed existence of various objects like the thermodynamic formalism for the closed random co-cycle.
What about the statistic of it in time?
Well, this is the result. maybe it's not too exciting, but I mean, in a way, it's a cheap corollary of what we have. Yeah, it's if you yeah. Yeah, so far we assumed existence of thermodynamic formalism for the closed random co-cycle, and our extreme value theory needs, and our perturbation theory needs, these nice equivariant top spaces of measures and functions in order to run the abstract theory and then finally get the all the following results. So if we want to work with examples, we have to have suitable hypotheses that tell us that the closed map co-cycle has a thermodynamic formalism, and then we need some hypotheses and a theory to say when you puncture with holes, you still have a thermodynamic formalism. So I already mentioned that there was this, the paper we have out that would work for item 1. And in fact, this has several examples, and even with non-uniform expansion and countable branches. But we need a little bit more uniformity for the extreme value theory, and so rather than use this more complicated paper, we go back to this paper, which has simpler, in quotes, techniques, but it was dealing just with this weight, and you can, I guess all the machinery is really there, and you can, with not too much trouble, extend that to contracting weights, and then in a more uniform setting, you get everything that you want. So that takes care of item 1. That's how we do it in the paper I'm talking about today. And now foreshadowing what's coming on the next slide, which is the persistence of a thermodynamic formalism when you inject holes. Here are the hypotheses we need. So these are the map hypotheses. I let you read the first one. The second one is boundedness of derivatives and degree, and you should be uniformly covering. Your weight hypotheses, you should be uniformly bounded above and below. And finally, this is the contracting condition in the random setting. And our whole hypotheses, this is what is uniform covering? That the number of iterates, so you have your small interval j and you want to iterate to cover or to get above an indicator function of a certain height, and so it means uniform in omega. So the k, the number of iterates you need, is not depending on omega. So this may answer Matt's question about holes. So we need a uniform upper bound on the number of connected components of the holes.
Yeah, I guess so. Your functions are maximized with a finite number of points or something like
that. And the hole size should go to 0. And when your holes are small, then every map is surjective. Okay, then from the setting where you have a closed thermodynamic formalism, you can on each fiber insert small holes everywhere randomly, and now you have an open system, and your open system has a thermodynamic formalism as well, which is very nice. So I think I just said all the dot points here. You get all these objects that you want. So insertion of sufficiently small random holes to our closed map co-cycle leads to all of these things, all the things that you would have in the closed case. Because we have this uniformity, the multipliers and the densities are bounded above and below uniformly. You can view this as generalizing the Livrani-Momme-Deschamps 03 result from a deterministic map to the random case. So in this 2003 paper, you assume a closed thermodynamic formalism for a map, and you stick in some small holes, and they show that this persists. So this is the analog of that. And a key ingredient to this proof is a result of a former PhD student of mine, Harry Crimmins, who has this very nice result on stability of uniformly hyperbolic oscillated spaces. So what we're doing, a main part of this result, is just interpreting that in terms of only the top oscillated spaces to get our thermodynamic formalism. Okay, I guess I have, Mr. Chairman, 4 minutes. Okay, let's see. Okay, so our framework is fairly general, but here is one specific application. So we think about random beta maps. Beta can be anything bigger than 2, except it should not be just a little bit above an integer, because the uniform covering, for example, we need to satisfy that, and so we ask that there's some delta, and the betas are always more than delta above an integer. And so this means you don't have some tiny branch at the end, and so you don't have arbitrarily small branches. So arbitrarily small branches would kill the uniform covering. Your base dynamics can be pretty much whatever you like. Can be rotation, doesn't need to be mixing. Yeah, in this paper that I mentioned a couple of times, we show, in fact, it has this example, and we show it has a random thermodynamic formalism. And the closed system is already rather complicated, right? You can have countably many discontinuities of your invariant densities and so on. So now what we do is think about introducing small random holes on every fiber. And, well, the closed map cocycle and the weights, they already satisfy those set of conditions I had a few slides back. So when we choose our holes, they just have to satisfy the hole conditions, which are pretty general, so you can sprinkle the holes wherever you like, pretty much. And then the theorem C says that for this example, inserting small holes, essentially any way you like, won't destroy the thermodynamic formalism. So you have all these things which were there before. Now for the extreme value theory, now comes these Q's that we had. And I need to show that as epsilon goes to 0, these numbers converge to some other number. And in the absence of other ideas, we just calculate these explicitly in the example. And because we have beta maps, and to make these calculations easier, you can think about observation functions that have a common maximum at the fixed point 0. So this means that you have holes that are in some small neighborhood of 0 for each of the maps. And this will imply that all of these are 0 for k not 0. So the only thing that is left, I mean, because these were conditional probabilities that you were in the hole, then you leave, and then you return after k steps. And if you're, for a fixed k, if you make your hole small enough, this is not possible. So the only one that's left is k is 0. And we just need to evaluate that. Okay, and then we have these scaling functions t, the observations h, which I already talked about, the thresholds and the scalings. And for this example, you can write down something reasonably explicit. So the t's, they're something you prescribe. Okay, pick your favorite random function t. That's what it is. And then, well, this is your theta. This is your theta omega. So previously this was e to the minus integral t omega theta omega. And here it has a specific form. The 0 is appearing because the holes are centered around the 0. That's why that's there. This is effectively, you have these two pieces. And this min is occurring because when you go from fiber to fiber, it might be that the hole size varies greatly from omega to sigma inverse omega, or it might be the holes are roughly similar size. So if they vary greatly, then the scaling kicks in, but if they're more commensurate, then you get information about the derivative or the leading oscillator's function.
This is the equivalent of the periodic case, right? 0 is fixed.
Yeah, but in the, well, so I wrote here, maybe this answers to some extent. So if I compare this to the deterministic setting, there you'd have a single beta map, you'd have a single observation function with a maximum at 0. Okay, Keller had this specific weight, which was the usual one. And you have a single scale factor, and the law would read like this. And you see it's very similar. I mean, you don't have the integral, but you have 1 minus beta. So this whole thing here, this min, would be replaced with the slope of the map. Possibly, yes, thank you. That one slipped through, yeah. Okay. Sorry?
What is the asymptotic of Zn?
The asymptotic of?
Zn.
Zn. Well, it's effectively captured by, I mean, it has to go like, it has to be chosen in such a way that the probability that you exceed the Zn should go like T over N. So there's no explicit. Yeah, so Matt, was it Matt? Yes, said there should be 1 over beta.
Yeah, 1 over beta.
Yeah,
1 over beta, yeah. Yeah.
But so that is the periodic case, right? So
well, for the fixed point in that case, yes.
Yeah, but a periodic it would be 1, right?
That is right, yes.
So
yes.
in the random, maybe 1 is more easy because it's difficult to have periodic, right?
But isn't this coming because the k, I mean, there you have another k that is non-zero in the qk's.
Yeah.
That's the reason, right? So you have the 0 and the, yeah. And, well, here we just have the 0. So if we had another k for which we were non-zero, you would get some other contribution in the integral. So, and we did not look at that. It's too difficult. Oh, well, already it's long formula.
Why you can choose the so that this condition is satisfied?
The Zn, I mean, for the theorem, to get the law, you have to choose the Zn's in a particular way.
Yeah, but why it is possible?
You could ask the same question in the deterministic case. So, I mean, that's how the theory goes. I mean, people are interested in the thresholds themselves. Give you interesting information because if you want to have such an exponential law, then as an output, if you like, of the theorem, you get this sequence of Zn's. So you see how the Zn's have to, how they go toward the maximum of the observation with n. Yeah, I think Yuri's question was why should the Zn's behave in that way? Was that your question? Or?
Why you can choose the behaving in this way and why?
Yeah.
The measure is absolutely continuous, so you're choosing something else.
Okay.
Oh yeah, it is possible. It's it's possible. Oh, 1 minute. Okay. Oh, more than less than 1 minute. Okay. Okay. So anyway, I think I'm done now. So this is my summary slide, just summarizing what we did. So we had this abstract theorem, and then we looked at derivatives of escape rate, random extreme value theory, random hitting time statistics, and the last thing was about persistence of thermodynamic formalism when you inject holes. We also have quenched limit laws for contracting potentials, but I didn't talk about that. So all that's in this paper. And then, okay, this is my last slide. So we have, this team has 4 papers. I think we started over the last 4 years. I guess COVID did not help us socialize very much. So we just sort of stayed together. But so this was the one that was doing the closed case to show you have a random thermodynamic formalism for discontinuous maps. This is the large hole paper. This is what I talked about today. And this is somehow a blend of the first 2 with different, you don't need transitivity, but you pay for it with a strong, we use simpler cones, and the contracting condition turns out to be more, a little more severe, let's say. And I'm done now, thank you.